All right, so in this problem, we are given a telescope that's observing a supernova at a certain distance away, and we are trying to find that distance. So a couple of things that we are given is the amount of light energy during the first 10 seconds that is detected by the telescope. And we are also given the visible light power output of the supernova. And those are both during a period of 10 seconds. So we are trying to find how far the supernova is. So the first way to approach this problem is identify what we know. So that's going to be the light energy that's detected by the telescope and also the power output that's visible of the supernova. So that visible light power output of the supernova is 5.0 times 10 to the 37th watts. And as we said earlier, that is over that 10-second period. And we also know that the light energy that's detected by the telescope is 9.1 times 10 to the negative 11 joules. So we can use an intensity equation, which is equal to the power over the area, to find the intensity of that system. So we know that, so we're trying to find the intensity detected by the telescope. So we know for power, which is the light energy that's detected, so that was equal to 9.1 times 10 to the negative 11 joules. But we need to convert that into watts. So we know that so 1 joule per second is equal to 1 watt. So just to convert that, it's going to be that amount of joules that was detected over that 10-second period. So that's going to make it 9.1 times 10 to the negative 12th watts. And the area of that telescope is going to be, or the part that's observing it is just a circle, which is 4 pi, or sorry, not 4, pi r squared. And we know that the diameter of the telescope is 2.0 meters. And so because we're using an area formula, we're going to turn that into a radius, which is 1.0 meters. So we have the intensity detected by the telescope, which is trying to figure out equals the power, which is the light energy detected, and we converted that into watts earlier to get 9.1 times 10 to the negative 12 watts over the area of the telescope, which is going to be pi r squared, r being 1.0 meters from the 2-meter diameter, and that's going to equal 2.897 times 10 to the negative 12th watts per meter squared. So now, previously we identified the intensity detected by the telescope, and now we're going to try to find the intensity of the light from the Earth. And this is going to be important because eventually this R value we find is going to end up being the distance of the supernova from the telescope, which is what we're trying to find. So we already calculated that intensity from the previous equation, but now we're going to be trying to solve for R. So that power output, which we were given of the visible light for the supernova, was 5.0 times 10 to the 37th watts. And the area, which is the supernova, is a sphere, so that's going to be 4 pi r squared. So moving down, we already know the intensity equals the power over the area. So quickly we're going to isolate the R, and that's going to be the square root of the power over 4 pi times I, the intensity. Now, once we plug everything in, we're going to get the power, which was 5.0 times 10 to the 37th watts, and that was the power output of the visible light, over 4 pi times the previously calculated intensity, which was the intensity detected by the telescope. And that's going to give us an R of 1.17 times 10 to the 24th. But we need to convert into light years. So we know that 1 year is equal to 365 days. And we know that there are 24 hours in a day and 3,600 seconds in an hour. So we get 31,536,000 seconds in 1 year. And we know the speed of light is 3 times 10 to the 8th meters per second. So to calculate how far light would travel in a year, we would get 9.46 times 10 to the 15th meters. So we take that previously calculated R value, which is how far the supernova is, and convert into light years. In light years, that ends up being 1.24 times 10 to the 8th light years. So just some of the tricky parts is knowing which intensity, I guess, corresponds to what part of the system. Also knowing to convert that given value of the joules for the light observed, the energy of the light observed from the telescope, and converting that into watts. And yeah, just knowing, well, understanding the parts of the system between the telescope and the supernova, and knowing which part goes to where. And that was just some of the tricky parts. And this just has to relate with just using like an intensity equation, using like a systems-based thinking method. And yeah, that was pretty much it.